From the motion of planets to the behavior of subatomic particles, we've built theories that explain much of the world around us. Yet, at the heart of it all lies a perplexing problem. The laws of physics, as we know them, don't fit together. Einstein's general relativity describes the universe on the grandest scales, from galaxies to black holes, while quantum mechanics governs the strange, probabilistic world of the very small. But when these two pillars of modern science collide, such as near the core of a black hole or at the universe's birth, the equations break down. Enter string theory, a bold and ambitious idea that seeks to unite these two worlds into a single theory of everything. At its core, string theory suggests that the universe is made of tiny vibrating strings of energy. These strings, and their unique vibrations, could explain everything from gravity to the behavior of electrons. But what are these strings made of? Why do we need extra dimensions? And could string theory ever be proven? Join me as we uncover the biggest mystery of the cosmos. The birth of a revolutionary idea, how string theory began. In the mid-20th century, physics was at a crossroads. Two great theories, quantum mechanics and general relativity, had revolutionized our understanding of the natural world, but they did not agree. Quantum mechanics described the behavior of particles and forces at incredibly small scales, while general relativity explained the curvature of space and time under the influence of massive objects. Each worked perfectly in its domain, but when physicists tried to merge them, the mathematics broke down. There was chaos instead of harmony. This tension drove scientists to look for something deeper. They imagined there might be an underlying framework that could bridge these worlds. That search, however, did not lead directly to string theory. In fact, string theory began almost by accident, and not even as a theory of everything. It started as an attempt to explain something much more specific, the strange behavior of particles known as hadrons. Hadrons were at the center of experimental physics in the 1960s. These particles, which include protons and neutrons, were found to interact through the strong nuclear force, the force responsible for holding atomic nuclei together. Experiments revealed that hadrons were not fundamental particles. Instead, they seemed to be made of smaller constituents, but their behavior was puzzling. Physicists struggled to explain the patterns seen in particle collisions and the relationships between different types of hadrons. In this climate of confusion, an unexpected discovery was made. A young physicist named Gabriele Veneziano stumbled upon a peculiar mathematical function while working at CERN in 1968. This function, known as the Euler beta function, seemed to describe the complex interactions between hadrons. The beta function matched experimental data remarkably well, but nobody knew why it worked. It was a mathematical mystery. Veneziano's work sparked a wave of interest. Physicists began to explore whether this function could hint at something deeper. Soon, it became clear that the beta function might have a physical interpretation. In 1970, two researchers, Leonard Susskind and Yoichiro Nambu, independently realized that the equations could be explained if hadrons were not point-like particles, but instead tiny, vibrating strings. This was a radical idea. In their vision, different vibrations of these strings corresponded to different particles. Much like different notes played on a violin string produced different sounds. This early version of string theory was elegant, but it had problems. For one, it predicted the existence of a particle with no mass that behaved like a graviton, a particle associated with gravity. At the time, this was seen as a flaw. String theory was meant to describe the strong nuclear force, not gravity. On top of that, the theory had mathematical inconsistencies that were difficult to resolve. Most physicists dismissed the theory as a curiosity, a detour on the path to understanding hadrons. Despite its initial rejection, a small group of researchers continued to explore string theory. In the early 1970s, the focus on hadrons shifted as physicists developed a more successful framework for the strong nuclear force called quantum chromodynamics, or QCD. With QCD in place, string theory lost its original purpose. It could have disappeared entirely, but then some physicists noticed that the graviton-like particle predicted by string theory wasn't just a mistake. Instead, it suggested that string theory might be something far more profound, a theory of gravity at the quantum level. This idea was ahead of its time. The mainstream physics community was not yet ready to embrace it. String theory languished on the fringes of scientific research for nearly a decade. It wasn't until the 1980s that string theory began to emerge as a serious contender for unifying all the forces of nature. New mathematical developments, including the discovery of supersymmetry, helped resolve some of its earlier inconsistencies. These innovations gave string theory a new lease on life, transforming it from a forgotten idea into a candidate for the much-desired theory of everything. The vibrating strings of physics. What early theories got right and wrong. The theory had early successes that captured the imagination of a few physicists. For example, it naturally accounted for the strong nuclear force. Using string theory, researchers could explain the behavior of hadrons in ways that traditional approaches struggled to match. It even hinted at the existence of particles that seemed to mediate forces, much like the known carriers of electromagnetic and nuclear forces. But the road wasn't smooth. Early string theory faced significant hurdles. One challenge came from the theory's mathematical structure. Early versions of string theory existed in a peculiar universe with 26 dimensions. This was an enormous leap from the familiar 4 dimensions of space and time. The idea of additional dimensions wasn't entirely new. Some physicists had proposed extra dimensions in the 1920s, but 26 seemed excessive and unrelated to anything observable. These extra dimensions weren't something that could be easily visualized or tested, making the theory feel abstract and disconnected from the real world. The theory also suffered from inconsistencies. The equations governing string vibrations sometimes produced nonsensical results, like probabilities greater than 100% or negative values for physical quantities. These errors hinted that the early formulations of string theory were incomplete, or that the idea itself might be fundamentally flawed. Many physicists moved on to other problems, leaving string theory on the fringes of research. Despite these setbacks, string theory had a few staunch supporters who believed in its potential. They saw its mathematical beauty and the way it connected seemingly unrelated aspects of physics. Over time, they began to refine the theory, addressing its weaknesses and exploring its deeper implications. One of the critical areas of refinement was understanding the role of the extra dimensions. Early work had treated these dimensions as mathematical curiosities, but later development suggested they might be physically real, just hidden from view. Physicists proposed that these dimensions could be compactified, curled up so tightly that they were imperceptible at everyday scales. This idea transformed what had seemed like a problem into a feature of the theory. It also opened up new questions about how these hidden dimensions could influence the behavior of strings and the particles they represented. Another breakthrough came with the introduction of supersymmetry in the 1970s. Supersymmetry was a bold hypothesis that paired each known particle with a superpartner, a new type of particle with related properties. When physicists incorporated supersymmetry into string theory, it resolved many of the mathematical inconsistencies that had plagued earlier versions. Supersymmetric string theory, or superstring theory, also reduced the number of required dimensions from 26 to 10. This made the theory feel more manageable and aligned it better with other approaches to unifying physics. These early successes also highlighted some missteps. One of the most significant was the tendency to oversimplify how strings vibrate. In the initial formulations, physicists assumed that strings vibrated in simple patterns, like plucking a guitar string, but real strings were far more complex. Their vibrations were influenced by the geometry of the extra dimensions, which acted like a stage, shaping the movement of the strings. Understanding this interplay required more sophisticated mathematics and deeper insights into the nature of space itself. Another misstep was underestimating the diversity of string configurations. Early researchers focused on single, isolated strings, but later work revealed that strings could interact, split, and merge in intricate ways. These interactions added richness to the theory, but also made it much harder to solve the equations. Physicists began to realize that understanding string theory fully would require not just mathematical skill, but also new tools and approaches. Despite these challenges, the idea of vibrating strings continued to captivate a growing number of researchers. They were drawn not just by the theory's promise, but by its underlying simplicity. If string theory were correct, it would mean that all of nature's complexity, the forces, particles, and even the fabric of space and time, could be explained as the result of strings vibrating in different ways. How string theory challenges Newtonian intuition. String theory challenges the way we've understood the physical world for centuries, overturning ideas that date back to Isaac Newton. Newton's laws of motion and universal gravitation shaped the foundation of classical physics, describing the behavior of objects with precision. These principles felt intuitive, grounded in everyday experiences of force, motion, and mass. Objects moved when pushed, fell under the pull of gravity, and their mass remained constant, no matter what. Space was an empty stage, and time ticked forward steadily, independent of everything else. One of the biggest ways string theory challenges Newtonian ideas is its view of particles and forces. In Newtonian physics, objects are solid, self-contained entities that interact through forces acting at a distance. String theory replaces these solid particles with tiny vibrating strings. This idea is radically different from Newton's view of particles as fixed points of mass. In string theory, mass isn't an inherent property of an object, but an emergent one. The energy of a string's vibration determines its mass, linking mass to the concept of energy in a deeply fundamental way. This relationship builds on Einstein's insight that mass and energy are interchangeable, but pushes it further by rooting both in the dynamics of strings. In this framework, what we think of as a particle's weight or heaviness is a direct result of how its string moves through spacetime. Newton described space as a vast, unchanging stage where events played out and time as a separate, constant flow. Even Einstein's general relativity, which bent and warped spacetime in the presence of mass and energy, preserved the idea that spacetime existed independently of the objects within it. String theory breaks even this connection. It suggests that spacetime might not be fundamental at all, but rather something that emerges from the interactions of strings. String theory describes additional dimensions of space that are curled up so tightly that they're invisible to us. These hidden dimensions shape the way strings vibrate and interact. The geometry of these dimensions influences everything we observe in our familiar three-dimensional world. This means that spacetime as we know it is only a part of a much richer and stranger structure. In classical physics, energy is a property of objects and systems, a measurable quantity that can be transferred or transformed but never lost. String theory ties energy to the fundamental structure of reality. The vibrations of strings create not only mass, but also the energy levels we observe. High-energy particles correspond to strings vibrating with more intensity or in more complex patterns. The energy of a system isn't just a property of objects within it, but a reflection of the vibrational states of the strings that make up those objects. String theory also redefines the idea of locality. In Newtonian physics, events happen in specific places, and their effects spread out from there. If you drop an apple, its motion is influenced by the gravitational pull of the Earth, which acts from a distance, but still within a defined framework of space. String theory blurs these boundaries. Because strings can stretch, split, and merge, their interactions can connect points in space that would otherwise seem unrelated. This non-locality challenges the classical notion that events have distinct causes and effects confined to a particular region. Discovering the mathematical landscape of strings. The development of string theory has revealed a mathematical landscape that is both intricate and beautiful, a world where abstract structures guide our understanding of the universe's deepest workings. Unlike classical physics, which often describes physical phenomena with relatively straightforward equations, string theory relies on advanced mathematics, not merely to explain what is observed, but as the foundation for its very existence. The mathematics required to describe these strings goes beyond the familiar realms of algebra or calculus, delving into areas like differential geometry and topology. These branches of mathematics deal with the properties of shapes and spaces, providing tools to understand the complex multidimensional spaces that string theory depends on. Strings exist in a universe with many more dimensions, all tightly folded into intricate geometries. One of the most important mathematical objects in string theory is the manifold. Manifolds are spaces that locally resemble familiar Euclidean geometry, but can have vastly different global structures. In string theory, the extra dimensions of spacetime are often modeled as manifolds. These aren't random shapes. Their properties directly affect how strings vibrate, which in turn determines the physical characteristics of particles. For instance, the shape and size of these manifolds influence the masses of particles and the strengths of the forces between them. Among the most famous examples of these manifolds are Calabi-Yau spaces. These are six-dimensional structures that are compactified, folded in on themselves so tightly that they remain hidden from our everyday perception. Calabi-Yau spaces possess a property called Ricci flatness, which means they have zero curvature in a specific sense. This property makes them suitable for string theory, as they allow for stable vibrational modes of strings. The discovery of these manifolds was not a direct result of physical experimentation, but of mathematical exploration. Mathematicians studying complex geometry had developed the theory of Calabi-Yau spaces independently of string theory. When physicists realized that these mathematical objects could describe the hidden dimensions required by string theory, it underscored the deep connection between abstract mathematics and fundamental physics. This was not the first time such a connection had been revealed. Einstein's general relativity had also relied on advanced mathematics, particularly Riemannian geometry. Another key mathematical structure in string theory is group theory, which studies symmetries. In physics, symmetries often correspond to conserved quantities or fundamental forces. For example, the symmetry of a system under rotation implies the conservation of angular momentum, while gauge symmetries underlie the electromagnetic, weak, and strong nuclear forces. String theory extends these ideas by requiring even more intricate symmetries, some of which are tied to the theory's consistency. Supersymmetry is one such symmetry. It relates particles of matter, like electrons and quarks, to particles that mediate forces, like photons and gluons. Mathematically, supersymmetry is described using algebraic structures that extend traditional group theory. These structures, called Lie superalgebras, encode the relationships between particles and their superpartners. The richness of the mathematical landscape in string theory becomes even more apparent in its treatment of dualities. Dualities are surprising correspondences between seemingly different physical theories. For instance, T-duality shows that a string compactified on a small circle behaves in the same way as a string compactified on a large circle, with the radius of one circle inversely related to the other. This reveals that the size of extra dimensions is not an absolute concept, but something that can change depending on the perspective. Another example is S-duality, which connects strong and weak coupling regimes of a theory. In string theory, when the interactions between strings are strong and complex, the theory can often be reformulated in a way that makes those interactions weak and easier to calculate. These dualities suggest that our descriptions of the universe are not unique, and that different mathematical frameworks can describe the same physical phenomena. Classical general relativity predicts that black holes are singularities, where space-time curvature becomes infinite. String theory, however, suggests that strings can smooth out these singularities. replacing them with finite structures. The mathematics of string theory has even been used to calculate the entropy of black holes, linking the theory to thermodynamics and statistical mechanics. These calculations rely on advanced techniques from geometry, algebra, and number theory. Despite its successes, the mathematical complexity of string theory has also been a source of criticism. Some argue that the theory is so dependent on abstract mathematics that it risks losing its connection to physical reality. Unlike traditional scientific theories, which are often tested through direct experiments, string theory operates at scales and energies far beyond what current technology can probe. This has led to debates about whether string theory should be considered a physical theory or a mathematical framework that awaits future validation. Strings as the universe's fundamental building blocks, beyond particles. The idea of particles as point-like objects has been a cornerstone of physics for much of its history. In quantum field theory, particles are treated as zero-dimensional points, mathematical entities with no size or structure. This approach works remarkably well for describing many aspects of particle interactions, such as how photons mediate electromagnetic forces, or how quarks are bound together inside protons and neutrons. But as scientists pushed the boundaries of what quantum field theory could explain, cracks began to appear in the framework. Certain calculations, especially those involving very high energies or extremely small scales, led to infinities that defied physical meaning. String theory offers a radical solution to this problem by replacing point-like particles with one-dimensional strings. These strings are unimaginably small, on the order of the Planck length, which is about 10 to the power of minus 35 meters. At this scale, the very concept of size, as we understand it, becomes difficult to grasp. This shift from points to strings solves some of the most perplexing issues in quantum field theory. One of the major problems with point-like particles is that their interactions at very short distances lead to infinities in the equations. For example, when two particles interact, the closer they get, the stronger their interaction becomes in the mathematics of quantum field theory. At zero distance, when the particles are treated as points, the strength of the interaction becomes infinite, and the equations break down. This issue, known as a divergence, has long plagued physicists trying to reconcile quantum mechanics with the force of gravity. Strings, however, do not suffer from this problem. Because they are not points, they cannot approach each other infinitely closely. When two strings interact, their interactions are spread out over a tiny but finite region of space. This smearing effect removes the infinities that arise in point-particle calculations. Instead of breaking down at short distances, the equations of string theory remain well-behaved, offering a consistent framework for understanding particle interactions, even at the highest energies. The transition to strings also provides a natural way to incorporate gravity into quantum theory. In traditional quantum field theory, gravity has always been the outlier among the fundamental forces. While the electromagnetic, weak, and strong nuclear forces can all be described within the framework of the Standard Model, gravity stubbornly resists quantization. Attempts to create a quantum field theory of gravity lead to equations filled with unmanageable infinities. String theory circumvents this issue by showing that gravity emerges naturally from the vibrations of strings. One specific vibrational mode of a string corresponds to the graviton, the hypothetical particle that mediates the force of gravity. In the point particle view, forces are mediated by the exchange of particles like photons, gluons, and W and Z bosons. These particles are described as being emitted and absorbed by other particles, creating the forces we observe. String theory reimagines and claims that when two strings come close, they can split, merge, or vibrate in new ways, creating the effects we perceive as forces. In quantum field theory, each force and particle requires its own set of rules and parameters. The electromagnetic force is described by quantum electrodynamics, or QED, while the strong nuclear force is governed by quantum chromodynamics, or QCD, and so on. Each of these theories is highly successful in its domain, but combining them into a single framework has proven elusive. String theory offers a way to unify these forces by showing that they all emerge from the same fundamental objects. Another feature of strings is their ability to connect distant parts of spacetime. In the point particle view, interactions are local. Particles influence each other only when they are in close proximity or through the exchange of force-carrying particles that travel between them. Strings, however, can stretch and loop, linking regions of spacetime that would otherwise seem disconnected. The 5 flavors of string theory. Are they all different? When string theory first emerged, it didn't present itself as a single unified framework. Instead, it appeared in 5 distinct forms, each with its own set of equations, characteristics, and assumptions. These 5 flavors of string theory seem to describe different physical realities. The discovery of these separate formulations initially caused confusion, but eventually revealed a deeper structure underlying them all. The 5 types of string theory are named based on the mathematical features they emphasize: Type 1, Type Ni-A, Type Mi-B, and 2 heterotic versions called the heterotic SO, 32, abbreviated as HO, and heterotic E8, abbreviated as HE. These theories differ in their assumptions about the strings themselves, whether they are open or closed, oriented or unoriented, and in the kinds of symmetries they respect. Type 1 string theory incorporates both open and closed strings. Open strings have 2 endpoints, while closed strings form loops. The inclusion of both types allows Type 1 theory to describe interactions that are unique compared to the other formulations, which generally focus on closed strings. Type 1 theory also includes a feature called orientation reversal, meaning strings can flip directions as they vibrate, adding an additional layer of symmetry to the theory. Type TTA and Type WB theories deal exclusively with closed strings, but differ in their treatment of supersymmetry. In Type TTA theory, the supersymmetry is non-chiral, meaning it treats left-handed and right-handed states of particles symmetrically. Type WB, in contrast, is chiral, giving different treatment to these states. This distinction leads to differences in the mathematical properties of the 2 theories and the kinds of physical phenomena they can describe. The 2 heterotic string theories, HO and He, are unique in that they combine 2 very different types of strings. On one side, the strings behave like those in traditional bosonic string theory, which describes vibrations associated with forces and particles. On the other, the strings incorporate supersymmetry, allowing them to include fermions, the building blocks of matter. Their names are derived from the mathematical structures, or symmetry groups, that define how the strings vibrate and interact. These groups represent the internal symmetries of the strings, governing how they connect to the forces and particles we observe. Initially, these 5 theories seemed distinct, and it wasn't clear why there were multiple versions of a theory claiming to describe everything. Physicists began to wonder if some or all of the theories were incomplete, or if they were describing entirely separate realities. On one hand, each theory seemed internally consistent and capable of describing certain aspects of the universe. On the other hand, their coexistence hinted at a larger, yet-to-be-discovered framework. The breakthrough came in the mid-1990s, during a period now known as the second superstring revolution. Researchers discovered that the 5 string theories were not truly separate, but were instead different perspectives of a single underlying theory. This unifying framework came to be known as M-theory, though the M has never been definitively defined. Some suggest it stands for membrane, mother, or even mystery. The unification of the 5 string theories under M-theory was made possible by the discovery of dualities, mathematical relationships that connect seemingly distinct theories. For example, T-duality showed that type TKNA and type TWERY-B string theories are connected in a surprising way. If one theory describes strings vibrating in a space where one dimension is very small, the other describes the same physics in a space where that dimension is very large. This equivalence revealed that the distinction between the two theories was not fundamental, but a matter of perspective. Another duality, S-duality, connected the HO and He theories with type 1 string theory. S-duality shows that when one theory describes strong interactions between strings, the other describes weak interactions, and vice versa. This relationship allowed physicists to use one theory to make calculations in regimes where the other theory becomes mathematically intractable. Perhaps the most profound insight came from the realization that M-theory requires not just strings, but also higher dimensional objects called branes. These branes, which can have 2, 3, or more dimensions, expand the idea of fundamental building blocks beyond one-dimensional strings. For example, a two-dimensional brane, or membrane, might look like a vibrating sheet, while a three-dimensional brane could resemble a volume of space. These branes introduced entirely new dynamics to the theory, showing that strings could exist as part of a richer and more complex universe. In this new framework, the 5 flavors of string theory are understood as different slices of M-theory, each describing a particular aspect of its broader structure. The 10 dimensions of the original string theories become part of an 11-dimensional space-time in M-theory, with the extra dimension allowing for the inclusion of branes. This 11th dimension provides the space in which strings and branes interact, creating the phenomena we observe in lower dimensions. The role of supersymmetry in string theory's framework. Supersymmetry is one of the most essential ideas within the framework of string theory. At its core, it is a mathematical symmetry that links two fundamentally different types of particles: fermions, which make up matter, and bosons, which carry forces. This connection between matter and force particles is not something seen in the standard model of particle physics, where fermions and bosons are treated separately. Supersymmetry suggests that for every fermion there exists a corresponding boson, and for every boson there exists a corresponding fermion. These pairs are called superpartners, and their existence would fundamentally alter the way we understand the universe at its smallest scales. Without supersymmetry, many of the equations that describe string theory would not work properly. String theory requires a delicate balance between the vibrations of strings to prevent mathematical inconsistencies, such as infinities or negative probabilities, from appearing in the calculations. Supersymmetry provides this balance by ensuring that every vibration of a string, whether it corresponds to a fermion or a boson, contributes in a way that keeps the theory stable. By incorporating supersymmetry, string theory became superstring theory, a far more robust theoretical model than its predecessors. In the standard model, fermions include particles like electrons, quarks, and neutrinos, which are the building blocks of matter. Bosons include particles like photons, gluons, and the Higgs boson, which mediate the forces of nature. These two groups of particles have very different properties. Fermions obey the Pauli exclusion principle, meaning no two fermions can occupy the same quantum state at the same time, while bosons do not have this restriction and can clump together in the same state. In a supersymmetric universe, every known particle would have a superpartner. For instance, the electron, a fermion, would have a superpartner called the selectron, which would be a boson. Similarly, the photon, a boson, would have a superpartner called the photino, which would be a fermion. These superpartners would share many properties with their known counterparts, such as charge and spin, but they would differ in mass and in how they interact with other particles. One of the theoretical appeals of supersymmetry is that it helps to solve some of the biggest puzzles in physics. One of these puzzles is the hierarchy problem, which involves the enormous difference in scale between the weak nuclear force and gravity. In the standard model, the Higgs boson's mass is highly sensitive to quantum corrections from virtual particles, leading to calculations that suggest it should be far heavier than it actually is. Supersymmetry provides a natural solution by introducing superpartners that cancel out these corrections, keeping the Higgs mass at its observed value. Despite its theoretical elegance, supersymmetry faces a major challenge: experimental evidence. As of now, none of the predicted superpartners have been observed in experiments. This absence is particularly striking because if supersymmetry exists at the energy scales currently accessible to particle accelerators like the Large Hadron Collider, aka the LHC, we should have detected at least some of these superpartners by now. The failure to find evidence for supersymmetry at these energy levels has led some physicists to question whether the symmetry is realized in nature or if it exists at energy scales far beyond our current reach. One possible explanation for the lack of observed superpartners is that supersymmetry is a broken symmetry. In physics, symmetries can be broken in such a way that they still influence the underlying structure of a theory but do not appear directly in the observable world. For example, in the early universe, supersymmetry might have been an exact symmetry, meaning every particle had a superpartner with the same mass. As the universe cooled, this symmetry could have broken, causing the superpartners to become much heavier than their known counterparts. If the masses of the superpartners are far beyond the energy scales we can probe, their effects would be subtle and indirect, making them harder to detect. The search for supersymmetry continues to be a major focus of experimental physics. Physicists are not only looking for superpartners, but also for indirect evidence of supersymmetry's effects on other processes. For example, supersymmetry predicts specific patterns in how particles decay, and it could influence the behavior of dark matter, the mysterious substance that makes up most of the matter in the universe. Some versions of supersymmetry suggest that the lightest superpartner could be a candidate for dark matter. Supersymmetric equations have deep connections to many areas of mathematics, particularly in geometry and topology. For instance, supersymmetry has led to new insights into the geometry of Calabi-Yau manifolds, the shapes of the extra dimensions in string theory. While the lack of experimental evidence for supersymmetry has been a source of frustration, it has not diminished its theoretical appeal. Supersymmetry remains a cornerstone of string theory, providing the consistency that the theory needs to describe the fundamental workings of the universe. Why tension matters: the physics of string vibrations. In string theory, the concept of tension is fundamental. At first glance, the term might seem simple, like the tension in a rope or an elastic band, but in string theory, it is one of the most important properties of the universe's smallest building blocks. The tension of a string determines how it vibrates, and those vibrations, in turn, define the properties of particles. Unlike particles, which are treated as points with no dimensions, strings have a one-dimensional structure, meaning they have length but no width. They can be open, with two ends, or closed, forming a loop. Despite their tiny size, strings are not passive. They are dynamic, constantly vibrating in complex patterns. These vibrations are not random. They are governed by the string's tension, which acts like the stiffness of a violin string. The higher the tension, the higher the energy required to set the string vibrating. The tension of a string is directly tied to the energy scale of its vibrations. In classical physics, we often think of energy in terms of motion or heat, but in string theory, energy is intrinsic to the string's vibrations. A string under high tension resists movement, requiring a significant amount of energy to excite. This energy is not just a detail, it determines the string's vibrational modes. Each mode represents a distinct way the string can oscillate, and each oscillation is linked to a specific particle with particular properties. For example, one vibrational mode might correspond to a photon, while another might correspond to a quark. The same string can produce an entirely different particle by vibrating in a different way. The tension of the string defines the range of possible notes, or in this case, the types of particles it can represent. In classical music, the pitch of a string's vibration depends on its length, tension, and the density of the material. Similarly, in string theory, the tension determines the fundamental frequency of the string's vibrations. However, string theory operates on an entirely different energy scale. The tension of these strings is thought to be incredibly high, far beyond anything we can experience in everyday life. This high tension is one of the reasons why strings are so small. They require immense energy to vibrate, and their size is inversely proportional to their energy scale. The higher the energy, the smaller the size of the string. Unlike the three spatial dimensions and one time dimension we experience, string theory posits the existence of additional dimensions, often compactified into tiny shapes. These extra dimensions influence the vibrational patterns of strings, much like the shape of a drum affects the sound it produces. For example, the properties of fundamental particles, such as their masses and charges, depend on how strings vibrate within the geometry of these extra dimensions. Changing the shape or size of the compactified dimensions would alter the vibrational modes, potentially leading to a completely different set of physical laws. In this way, the tension of strings is intimately connected to the structure of space-time itself. From the macroscopic to the microscopic, reconciling general relativity with quantum mechanics. Both general relativity and quantum mechanics work exceptionally well in their respective domains, but they clash when pushed to the limits. String theory has emerged as one of the candidates for reconciling these two views, offering a way to unify the macroscopic and the microscopic into a single framework. One of the major issues arises at the Planck scale, the realm where quantum effects and gravitational effects are equally strong. This scale, unimaginably tiny at about 10 to the power of 35 meters, represents a regime where our current theories break down. General relativity, which describes spacetime as smooth and continuous, fails to account for the quantum fluctuations that dominate on this scale. Similarly, quantum mechanics struggles to incorporate gravity without producing nonsensical infinities. Instead of treating particles as point-like objects, string theory proposes that the smallest constituents of matter and energy are one-dimensional strings. This shift in perspective eliminates many of the issues that arise when trying to combine general relativity and quantum mechanics. General relativity treats spacetime as a smooth continuum that bends and warps in response to mass and energy. Quantum mechanics, however, suggests that on the smallest scales, spacetime might not be smooth at all, but instead behaves chaotically with constant fluctuations. String theory reconciles these views by suggesting that the apparent chaos of spacetime at the quantum level is smoothed out by the presence of strings. The extended nature of strings prevents the infinities that arose previously, providing a natural cutoff to the quantum fluctuations. This smoothing effect is particularly important when it comes to understanding black holes. In general relativity, at the center of a black hole lies a singularity, a point where density becomes infinite and the equations of general relativity break down. Quantum mechanics predicts that such infinities should not exist, but it cannot fully describe what happens near a singularity. String theory replaces the concept of a point-like singularity with a network of strings, avoiding the infinities and providing a more complete picture of black hole interiors. Another way string theory reconciles these two frameworks is through its treatment of spacetime dimensions. General relativity and quantum mechanics operate in 4 dimensions. String theory requires additional dimensions, which provide the mathematical flexibility needed to merge general relativity with quantum mechanics. Without these extra dimensions, the unification of gravity and quantum mechanics would be mathematically impossible. One of the most compelling aspects of string theory is its ability to resolve certain paradoxes. For example, Hawking radiation, a phenomenon predicted by quantum mechanics, suggests that black holes can emit particles and eventually evaporate. This process creates a tension with general relativity, which implies that information about what falls into a black hole is lost forever. This apparent loss of information violates a fundamental principle of quantum mechanics, leading to what is known as the black hole information paradox. String theory, with its network of strings and extended structures, offers a potential resolution by showing how information could be preserved in the vibrations and interactions of strings, even as a black hole evaporates. The probabilistic nature of quantum mechanics also aligns with string theory's framework. In traditional quantum mechanics, particles can exist in a superposition of states, and their behavior is described by probabilities rather than certainties. String theory extends this idea by allowing strings to vibrate in multiple modes simultaneously. These modes are influenced by the geometry of spacetime, including the compactified dimensions. The result is a richer and more complex probabilistic structure that reflects the interplay between quantum mechanics and general relativity. The graviton and string theory's role in explaining gravity. The graviton is a theoretical construct meant to explain how gravity operates on a quantum level, much like photons mediate the electromagnetic force. Unlike the electromagnetic weak and strong nuclear forces, which have been successfully described within the framework of quantum field theory, gravity has resisted such treatment. To understand how the graviton emerges in string theory, it's important to begin with the idea of string vibrations. The graviton corresponds to a specific vibrational mode of a closed string. Closed strings are loops, as opposed to open strings which have endpoints. This loop structure is critical because it allows the graviton to exhibit the properties needed to mediate gravity. The graviton is predicted to have no mass, a property that aligns with our understanding of gravity as a long-range force. A massless particle can travel an infinite distance without losing energy, which is consistent with the fact that gravitational effects can be felt across vast stretches of the universe. Additionally, the graviton has a specific quantum property known as spin, which in this case is equal to 2. This spin value is essential because it reflects the tensor nature of gravity. In general relativity, gravity is not just a force acting between two masses, but a geometric phenomenon that bends spacetime. A spin-2 particle like the graviton is capable of encoding the complex interactions required to describe such curvature. When physicists examine the low-energy behavior of string theory, meaning scenarios far removed from the extreme conditions of the Planck scale, they find that it reproduces the equations of general relativity. In other words, string theory contains Einstein's theory as a special case. This connection is a profound result because it shows that string theory is not a replacement for general relativity, but an extension of it. While general relativity works beautifully to describe gravity on large scales, string theory goes further by providing a framework for understanding gravity at the smallest scales, where quantum effects cannot be ignored. When physicists try to quantize gravity using traditional quantum field theory methods, they encounter infinities that cannot be resolved. These infinities make calculations meaningless and indicate that something fundamental is missing from our understanding. String theory avoids these infinities. The graviton, as a vibrational mode of a string, fits seamlessly into this framework. During the first moments after the Big Bang, the universe was in a state of extreme density and temperature, where quantum effects would have played a dominant role in shaping spacetime. General relativity cannot describe these conditions, while string theory could potentially explain how gravity operated during this epoch. The graviton could help physicists unravel the mysteries of cosmic inflation, the rapid expansion of the universe in its earliest moments. Despite its theoretical appeal, the graviton remains elusive in experimental physics. Detecting a graviton directly is an extraordinary challenge due to its weak interactions. Gravitational waves, while easier to observe, provide only indirect evidence of the quantum nature of gravity. However, the absence of direct evidence does not diminish the importance of the graviton in string theory. It remains a cornerstone of the theory. Quantum foam and string theory, a dance of probabilities. Quantum foam arises from the principles of quantum mechanics, which dictate that even in a vacuum, energy cannot truly be zero. This residual energy, called zero-point energy, gives rise to fleeting virtual particles and waves that spontaneously form and vanish. These processes create a constantly shifting structure of spacetime. While this idea is key to understanding quantum fields, it poses significant challenges when applied to gravity. General relativity assumes a smooth, continuous structure, But on the scale of quantum foam, space-time behaves more like a stormy sea than a calm surface, and general relativity cannot handle this turbulent regime. String theory smoothens the chaos of quantum foam by introducing the dynamics of strings. Instead of point particles colliding and exchanging energy at infinitely small locations, strings interact over a finite area. This extended nature of strings effectively averages out the violent fluctuations of quantum foam, creating a more stable framework for understanding space-time. Strings do not eliminate the quantum nature of space-time, but reshape it in a way that can be mathematically described without breaking down into infinities. In quantum field theory, the unpredictable energy fluctuations of quantum foam can distort space-time in ways that are nearly impossible to calculate. These distortions might form microscopic black holes, or create wormholes connecting different regions of space-time. While these ideas are fascinating, they are also wildly unpredictable, making it difficult to develop a coherent theory. String theory offers a level of predictability by providing constraints on how these distortions can occur. The vibrational modes of strings define the types of particles and interactions that can exist. In string theory, space-time is not just a passive backdrop, but an active participant in the dynamics of strings. The properties of space-time, such as its curvature and dimensionality, influence the behavior of strings, and strings, in turn, affect the structure of space-time. This interplay helps tame the chaotic nature of quantum foam. For example, the extra dimensions predicted by string theory act as stabilizing elements, controlling the vibrations of strings and the interactions they produce. Another key insight from string theory is the concept of duality. Duality shows that certain descriptions of strings in one spacetime configuration can be equivalent to completely different descriptions in another configuration. This flexibility suggests that the chaotic fluctuations of quantum foam might be interpreted in multiple consistent ways within the framework of string theory. Duality provides a mathematical tool for understanding how quantum foam behaves across different energy scales and space-time geometries. In traditional quantum mechanics, energy fluctuations in the foam are highly localized and transient, making them difficult to analyze. The extended nature of strings spreads out these fluctuations, creating patterns that can be studied in greater detail. This spreading effect not only smooths out the infinities, but also reveals deeper connections between quantum mechanics and gravity. For example, the holographic principle, which emerges from string theory, suggests that the information contained within a region of spacetime can be encoded on its boundary. This offers a new way of thinking about quantum foam, where the chaotic interior might be described in terms of a simpler, lower-dimensional boundary. The multidimensional universe. What are the extra dimensions? In the universe we experience daily, space appears to have 3 dimensions: length, width, and height. Time adds a 4th dimension, creating what physicists refer to as spacetime. This 4-dimensional framework underpins most of modern physics. The concept of extra dimensions is not entirely new. It was first proposed in the early 20th century by Theodore Kaluza and Oscar Klein in an attempt to unify gravity and electromagnetism. They suggested that an additional dimension, curled up so small it couldn't be observed, could explain the electromagnetic force as a geometric property of spacetime, similar to gravity. Though this idea faded for decades, it was revived in the context of string theory, where extra dimensions became a cornerstone of the framework. The idea of extra dimensions can seem strange, but it arises naturally in string theory. Strings, as one-dimensional objects, vibrate and interact in ways that require a specific number of dimensions to avoid contradictions in the equations that describe them. In the earliest versions of string theory, calculations revealed the need for 26 dimensions, a number far beyond anything that matched observations. This discrepancy led to refinements in the theory, and with the incorporation of supersymmetry, the required number of dimensions was reduced to 10, 9 spatial dimensions and 1 of time. Later, developments in M-theory added yet another dimension, suggesting that the most fundamental version of string theory might operate in 11 dimensions. While these additional dimensions are necessary for the theory to work, why don't we see them in our everyday lives? The answer lies in the concept of compactification. According to string theory, these extra dimensions are not extended like the familiar ones, but are curled up into incredibly small shapes. These shapes are so tiny that they are effectively invisible to us. Imagine looking at a garden hose from a distance. It appears as a one-dimensional line. But upon closer inspection, you can see its circular cross-section, revealing a hidden dimension. Similarly, the extra dimensions in string theory are hidden because they are compactified at scales far beyond our ability to detect. The way these dimensions are folded and connected affects how strings vibrate. The different modes of vibration correspond to different particles, and the shape of the extra dimensions influences the range of possible vibrations. Physicists have proposed various shapes for these hidden dimensions, ranging from simple tori to complex structures like Calabi-Yau spaces. Calabi-Yau manifolds satisfy the mathematical requirements of string theory, while also offering a wide variety of configurations. These configurations provide the flexibility needed to describe the diversity of particles and forces in nature. However, the sheer number of possible shapes, estimated to be in the range of 10 to the power of 500, presents a significant challenge. Each shape represents a potential version of the universe, leading to the idea of a multiverse, where countless different universes exist, each with its own set of physical laws. The existence of extra dimensions also has implications for understanding gravity. One of the puzzles in physics is why gravity is so much weaker than the other fundamental forces. A common explanation in string theory is that gravity might spread out into the extra dimensions, diluting its strength in the three spatial dimensions we experience. This idea has been explored in models that propose large extra dimensions, where the compactified dimensions are relatively large compared to the Planck scale, but still small enough to escape direct detection. If true, this could lead to observable effects, such as deviations from Newton's law of gravitation at small distances, which experiments are actively testing. The Kaluza-Klein legacy, unveiling higher dimensions. In the early 20th century, long before string theory began to take shape, an idea emerged that hinted at the possibility of extra dimensions. This idea came from an attempt to unify two of the most important forces in physics, electromagnetism and gravity. It was called Kaluza-Klein theory, named after Theodor Kaluza and Oskar Klein, who independently developed the framework that would later inspire generations of physicists exploring the fabric of space-time. In 1919, Theodor Kaluza, a German mathematician, proposed a bold extension to Albert Einstein's general theory of relativity. Einstein had already shown that gravity could be understood as the curvature of four-dimensional space-time. Kaluza suggested adding a fifth dimension to this framework. His reasoning was not arbitrary. By extending Einstein's equations into 5 dimensions, Kaluza found that they naturally split into 2 distinct sets. One set described the familiar gravitational effects seen in general relativity, while the other closely resembled James Clerk Maxwell's equations of electromagnetism. This was a remarkable insight. It suggested that by introducing an extra dimension, 2 fundamental forces, gravity and electromagnetism, could be described using a single unified theory. At the time, unifying these forces was one of the grand challenges of physics. Kaluza's work appeared to provide a pathway forward, but if a 5th dimension exists, why don't we observe it in everyday life? This is where Oskar Klein's contribution became pivotal. In 1926, Klein proposed that the extra dimension could be compactified. Instead of extending infinitely like the familiar 3 dimensions of space, the 5th dimension could be curled up into a tiny circle, so small that it would be effectively invisible. Klein suggested that the extra dimension in Kaluza's theory was hidden at such a small scale that it escaped detection. Klein's idea of compactification was revolutionary, but it also introduced a challenge. If the fifth dimension was curled up, it implied the existence of specific energy levels associated with its size. These energy levels, called Kaluza-Klein modes, would manifest as new particles in the physical world. However, no experimental evidence of these particles was found at the time, leading to skepticism about the theory. In the decades that followed, the scientific community largely set Kaluza-Klein theory aside. Quantum mechanics was rapidly advancing, and the focus shifted toward understanding the behavior of particles and forces within the framework of the Standard Model. Yet, the foundational ideas of Kaluza and Klein did not disappear entirely. They resurfaced in the 1970s and 1980s, when physicists began to explore string theory as a candidate for unifying all fundamental forces. The influence of Kaluza-Klein theory on string theory was not limited to the idea of compactification. It also provided a conceptual blueprint for unifying forces through geometry. In Kaluza's original work, gravity and electromagnetism were unified by extending Einstein's geometric description of spacetime into an extra dimension. String theory took this idea to a new level, suggesting that all forces and particles could arise from the vibrational modes of one-dimensional strings moving through a multi-dimensional spacetime. One of the most compelling aspects of Kaluza-Klein theory was its ability to introduce quantum-like behavior through its compactified dimension. The discrete energy levels associated with the fifth dimension mirrored the quantization observed in atomic spectra, providing a tantalizing hint that geometry and quantum mechanics might be fundamentally connected. String theory built on this insight, using the compactified dimensions to explain how strings could give rise to the diverse array of particles observed in nature. The equations governing the compactification of extra dimensions in string theory are deeply rooted in the techniques developed by Kaluza and Klein. Their work paved the way for exploring how higher dimensional spaces could influence lower dimensional physics, an idea that continues to drive research in quantum gravity and cosmology. While Kaluza and Klein's original framework has been superseded by more advanced theories like string theory and its higher dimensional generalizations, the core idea that the universe might have hidden dimensions that shape its physical laws endures. Calabi-Yau manifolds, the hidden shapes of string theory. In the world of string theory, the compactified dimensions of spacetime are not arbitrary. They are intricately structured and described by complex mathematical shapes known as Calabi-Yau manifolds. These multidimensional spaces are the hidden scaffolding upon which the universe's physical laws rest. Calabi-Yau manifolds are named after mathematicians Eugenio Calabi and Xingtong Yau. Calabi proposed the existence of these shapes, which have special geometric properties, while Yau proved they could exist within certain mathematical constraints. These manifolds have a unique balance of curvature that allows them to be flat in a very specific way, making them compatible with the equations of string theory. This mathematical flatness is crucial because it ensures that the compactified dimensions do not introduce inconsistencies into the physical laws we observe. To understand their significance, it helps to imagine these manifolds as a kind of microscopic landscape folded within each point of our three-dimensional space. If we were to zoom in far enough, beyond the limits of ordinary perception and measurement, we would find these extra dimensions compactified into shapes so small that they exist only at scales close to the Planck length. The geometry of a Calabi-Yau manifold determines the vibrational modes of strings, which in turn correspond to the fundamental particles of nature. The way these strings vibrate depends on the shape of the manifold they are wrapped around. The properties of these particles, such as their mass and charge, are directly influenced by the manifold's geometry. The manifold shape also dictates how strings interact with one another. Forces like electromagnetism and gravity arise from the exchange of particles, and the behavior of these particles depends on the compactified dimensions. For instance, the strengths of these forces are linked to the size and structure of the Calabi-Yau manifold. A slightly different shape could result in a universe with vastly different physical laws, perhaps one where atoms couldn't form or where gravity was too weak to hold galaxies together. Calabi-Yau manifolds are extraordinarily complex. They exist in 6 dimensions, folded within the familiar 3 spatial dimensions of our everyday experience. To visualize them, imagine twisting and curling a piece of paper into a complicated crumpled shape, but instead of 2 dimensions, it involves 6. This complexity makes it incredibly difficult to directly picture these shapes. But mathematicians use advanced equations and computer models to study their properties. These shapes are not unique. There are countless possible Calabi-Yau manifolds, each representing a different way to compactify the extra dimensions. This leads to an astonishing diversity of potential universes. The variety of possible manifolds is so vast that physicists refer to it as the string theory landscape. Each point in this landscape corresponds to a specific compactification, and by extension, a specific universe. The question of why our universe corresponds to one particular point in this landscape remains an open mystery in physics. Calabi-Yau manifolds also play a role in supersymmetry. Supersymmetry predicts that every particle has a partner, and the geometry of the Calabi-Yau manifold determines the properties of these partners. The manifold's symmetry properties ensure that the equations governing the interactions between particles remain consistent, even at the incredibly high energies where supersymmetry might become apparent. Despite their importance, Calabi-Yau manifolds are mathematical constructs, and their existence has not been directly confirmed through experiments. However, their role in string theory is so central that understanding these shapes better could unlock deeper insights into the nature of reality. Researchers are constantly refining their mathematical descriptions, using advanced tools from fields like algebraic geometry and topology to explore their properties. One of the challenges in studying Calabi-Yau manifolds is the sheer complexity of their equations. Even describing their simplest properties requires advanced mathematics far beyond what is used in most areas of physics. Yet, this complexity is also what makes them so fascinating. These manifolds encapsulate the idea that the universe is not just a physical entity, but also a deeply mathematical one, where the rules of geometry and symmetry govern everything from the smallest particles to the largest galaxies. Efforts to understand Calabi-Yau manifolds have also inspired developments in mathematics itself. The study of these shapes has led to new discoveries in areas like string dualities, from 10 to 11 dimensions, the M-theory connection. In the mid-1990s, string theory was at a crossroads. Decades of work had revealed 5 different formulations of the theory, each seemingly distinct but equally viable. These 5 theories shared a common foundation. However, the differences between them raised a number of questions. The turning point came in 1995 during a pivotal conference at the University of Southern California. Physicist Edward Witten presented a groundbreaking idea that would redefine the direction of string theory. Witten proposed that the 5 different versions of string theory were not separate theories at all. Instead, they were different limits of a single, more fundamental theory that existed in an 11-dimensional space-time. This theory became known as M-theory. String theory had long relied on the existence of 10 dimensions, 4 that were observable and 6 that were compactified at scales far smaller than the limits of detection. These dimensions were necessary for the equations of string theory to be consistent. Adding an 11th dimension seemed to complicate the picture, but Witten and other physicists quickly showed that it simplified and unified the entire framework. In the new 11-dimensional picture, strings were no longer the only fundamental objects. M-theory introduced higher dimensional entities known as branes. These branes could have various dimensions, ranging from one-dimensional strings to two-dimensional surfaces, and even higher dimensional volumes. For example, a two-dimensional brane, often called a membrane, could stretch across space like a sheet, while a three-dimensional brane might resemble a volume suspended in higher dimensional space. One of the key insights of M-theory was that the 5 previously distinct string theories could be understood as different perspectives on the same underlying structure. Depending on how the 11-dimensional spacetime was compactified, the equations of M-theory could be reduced to one of the 5 string theories. This unification provided a compelling explanation for the diversity of string theories and suggested that the apparent differences were the result of looking at the same theory from different angles. The introduction of the 11th dimension also resolved a long-standing puzzle in string theory. In the 10-dimensional framework, certain mathematical inconsistencies had suggested that the theory might be incomplete. By extending the theory to 11 dimensions, these inconsistencies vanished, and the equations became more robust. The additional dimension provided new ways to think about the interactions between strings and branes. In the 11-dimensional framework, the graviton emerged naturally as a vibration of a string in higher dimensional spacetime. This provided a strong theoretical link between M-theory and Einstein's general theory of relativity. By uniting the quantum world of strings with the geometric world of relativity, M-theory offered a potential solution to the long-standing challenge of reconciling quantum mechanics with gravity. The higher dimensional branes introduced by M-theory also opened up new possibilities for understanding the origins of the universe. In some scenarios, the Big Bang could be reinterpreted as a collision between 2 branes in higher dimensional space. This idea, known as the brane world cosmology, provided a novel way to think about the initial conditions of the universe and suggested that the familiar 4-dimensional spacetime we inhabit might be a kind of brane embedded in a larger, multi-dimensional reality. The inclusion of 11 dimensions also led to surprising connections with earlier theories of gravity. In the 1980s, physicists had studied a theory called 11-dimensional supergravity, which extended Einstein's equations to include supersymmetry. At the time, supergravity had been seen as a promising candidate for a unified theory, but it had fallen out of favor because it lacked the quantum mechanical framework needed to describe fundamental particles. M-theory revived interest in 11-dimensional supergravity, showing that it could be understood as a low-energy approximation of the more comprehensive string theory framework. Despite its elegance and unifying power, M-theory was, and remains, far from complete. While physicists have made significant progress in understanding its mathematical structure, the full details of the theory are still not well understood. One of the major challenges is the lack of a precise formulation for M-theory in 11 dimensions. Unlike the 5 string theories, which are defined by well-established equations, M-theory exists more as a conceptual framework than a fully developed theory. Another challenge lies in the sheer complexity of the higher dimensional mathematics involved in M-theory. The compactification of 11-dimensional spacetime onto intricate shapes like Calabi-Yau manifolds introduces a vast landscape of possible configurations. Exploring this landscape is an ongoing effort, requiring advanced mathematical tools and computational techniques. The holographic principle, a window into higher dimensional realities. In the 1990s, an idea began to reshape our understanding of spacetime and gravity, offering a glimpse into the mysterious relationship between dimensions. Known as the holographic principle, this concept emerged from attempts to make sense of black hole thermodynamics and quantum gravity. It suggested that the 3-dimensional world we experience might be a projection of a deeper, lower-dimensional reality. This idea, while sounding fantastical, has solid roots in physics and has become a cornerstone of modern theoretical frameworks, including string theory and M-theory. The origin of the holographic principle can be traced back to work by physicist Jacob Bekenstein and Stephen Hawking in the 1970s. Bekenstein proposed that the entropy of a black hole, the measure of disorder or information it contains, was not proportional to its volume, as one might expect. Instead, it was proportional to the surface area of its event horizon. Hawking expanded on this by showing that black holes emit radiation due to quantum effects near the event horizon, now known as Hawking radiation. Together, their insights hinted at a strange connection between a black hole's surface and its internal properties. This connection became a puzzle that physicists struggled to decode. If the information content of a black hole was determined by its two-dimensional surface area, rather than its three-dimensional volume, what did that say about the nature of spacetime itself? Gerard Hooft and Leonard Susskind took this idea further in the 1990s, proposing the holographic principle. They suggested that all the information within a given volume of spacetime could be encoded on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. The holographic principle gained significant traction through its connection to string theory, particularly in the work of Juan Maldacena in 1997. Maldacena proposed a concrete realization of the holographic idea through the anti-de Sitter conformal field theory correspondence, abbreviated as the ADS-CFT correspondence. This correspondence showed that a theory of gravity in a higher dimensional space, known as anti-de Sitter space, could be equivalent to a quantum field theory without gravity defined on its lower dimensional boundary. For instance, a five-dimensional gravitational theory could correspond to a four-dimensional quantum theory on the boundary of that space. This equivalence linked two seemingly different types of theories, one describing gravity and spacetime, the other describing quantum particles and fields. The implications were vast. For one, it provided a way to study quantum gravity indirectly. Since we lack a fully developed theory of quantum gravity, understanding it directly in higher dimensions is extremely challenging. However, the ADS-CFT correspondence allows physicists to study gravity by examining its equivalent quantum theory on the boundary, where the mathematics is often more tractable. This approach has been particularly useful in exploring the nature of black holes and understanding how they interact with quantum mechanics. The holographic principle also offered insights into the paradoxical behavior of black holes, known as the black hole information paradox. According to classical physics, any information that crosses the event horizon of a black hole is lost forever. But this contradicts quantum mechanics, which state that information cannot be destroyed. The holographic principle suggests a resolution by proposing that the information is not lost but encoded on the event horizon itself, preserved in a two-dimensional form. If the principle applies universally, it suggests that the entire universe could be viewed as a hologram, with all the information about the three-dimensional world encoded on a distant, lower-dimensional surface. The mathematical framework of the holographic principle has also proven useful in areas beyond high-energy physics. For example, researchers have applied holographic ideas to study strongly interacting systems in condensed matter physics, such as superconductors and quark-gluon plasmas. These systems are often too complex to analyze directly, but the holographic approach provides new tools for understanding their behavior. This cross-disciplinary applicability highlights the principle's potential as a unifying concept across different fields of physics. The universe's origins are often described using the Big Bang theory, where an incredibly dense and hot state expanded to form the cosmos we see today. However, the Big Bang raises questions about singularities, regions where densities and curvatures of spacetime become infinite. Traditional physics breaks down in such scenarios. The holographic principle offers a potential way around this problem. If the universe's information is encoded on a boundary, then the singularity might be an artifact of projecting higher dimensional data into three-dimensional spacetime. Instead of a true breakdown of physics, the Big Bang could represent a transition or transformation in how the boundary's information is expressed. This view could provide a more coherent understanding of the universe's origins and its initial conditions. Observational evidence for the holographic principle remains a challenge, but there are hints that it could have measurable effects. For example, researchers have explored whether the holographic nature of spacetime could leave imprints on the cosmic microwave background, the faint afterglow of the Big Bang. Tiny irregularities or patterns in this radiation might provide clues about the universe's underlying structure. Similarly, experiments in quantum gravity and high-energy physics could test predictions of holographic models, offering a way to validate or refute the principle. But if our universe is indeed holographic, what is the underlying mechanism that projects the higher dimensional world we observe? How do the extra dimensions of string theory and M theory fit into this picture? And if the holographic principle depends on the specific geometry of ad-s space, can it be generalized to describe our universe, which does not appear to have an anti-de Sitter structure? Dualities in string theory: how opposites reveal deeper truths. Dualities are one of the most surprising concepts to emerge from string theory. At first glance, they seem to suggest contradictions. How could two theories that look entirely different describe the same physical phenomena? Yet, this is exactly what dualities reveal. They show that the different formulations of string theory are not separate entities, but interconnected views of the same underlying reality. The idea of duality in physics is not entirely new. In classical physics, certain equations can have dual interpretations. For instance, the wave-particle duality in quantum mechanics tells us that light and matter can behave both as particles and as waves, depending on how they are observed. Similarly, in electromagnetism, electric and magnetic fields are two sides of the same coin, interconnected in Maxwell's equations. But the dualities found in string theory take this concept to a new level, suggesting equivalences between theories that seem fundamentally different in their mathematical structure and physical assumptions. One of the most well-known examples in string theory is T-duality. In simple terms, T-duality shows that the behavior of strings is equivalent in spaces with large and small dimensions. Imagine a string vibrating in a circular dimension, like a tiny looped path. If the radius of that dimension is very large, the string can move freely along it, and its vibrational modes reflect this freedom. But if the radius becomes extremely small, you might expect the string to be confined, unable to exhibit the same behavior. T-duality reveals that this isn't the case. The physics of a large radius and a small radius are interchangeable. A string in a small dimension can vibrate in ways that mimic its behavior in a large dimension, as if the two scenarios were reflections of one another. This equivalence is deeply counterintuitive. In everyday life, we think of size as an absolute quality. Something small cannot be mistaken for something large. But T-duality challenges this notion, suggesting that size in string theory is not an intrinsic property, but a relative one, depending on the vibrational modes of the strings. This has many implications for how we think about space itself, particularly the extra dimensions required by string theory. These dimensions might be so small as to be imperceptible, yet they are not invisible in the traditional sense. Their effects are encoded in the physics we observe, and their size may be interchangeable, with entirely different configurations. Another duality is S-duality, which relates the strength of interactions in one theory to the weakness of interactions in another. In many physical theories, the strength of interactions determines how particles or fields behave. Strong coupling means particles interact intensely, while weak coupling means they interact only slightly. These differences can make one version of a theory incredibly difficult to analyze while leaving another more tractable. S-duality bridges this gap by showing that a strongly coupled version of a theory can have an equivalent, weakly coupled description in another framework. In essence, it flips the roles, making the hard problem in one setting solvable in another. S-duality has been particularly important in the study of quantum field theories. It offers a way to understand phenomena that occur at high energies or in strong interaction regimes, where traditional methods fail. By translating these situations into their dual descriptions, physicists can use simpler mathematics to uncover truths about systems that would otherwise remain inaccessible. This duality is not just a mathematical trick. It points to a deeper unity in nature, suggesting that the strength of interactions is not a fundamental quality, but a relative one, depending on the perspective of the theory. The existence of multiple dualities led to one of the most significant discoveries in string theory: the unification of its 5 initial formulations: type 1, type DIT-A, type DIY-B, heterotic O, and heterotic E. Each was developed independently, with its own set of assumptions about strings, dimensions, and interactions. Initially, they appeared to be entirely separate theories, but as physicists explored dualities, they found that these theories were not separate at all. Instead, they were connected through webs of equivalences, each representing a different limit or perspective of a single, more comprehensive theory. These connections culminated in the development of M-theory, the landscape problem, infinite solutions, or a roadmap to the universe. The idea of a landscape in string theory refers to the staggering number of possible solutions that the theory allows for. In physics, a solution to a theory often describes a particular state of the universe, known as a vacuum state. Each vacuum state corresponds to a specific set of physical laws, particle properties, and forces. In string theory, these vacuum states arise from the many ways extra dimensions can be compactified, along with the vast variety of possible configurations for strings and their vibrations. This flexibility gives string theory its versatility, but also introduces a challenge that physicists call the landscape problem. Unlike simpler theories in physics, where there might be only one or a handful of solutions, string theory allows for an almost unimaginable number of possibilities. Estimates suggest as many as 10 to the power of 500 distinct vacuum states. This number is so large it defies comprehension. Each of these states corresponds to a potential universe, with its own set of physical constants, laws, and properties. Some might resemble our universe, while others would look completely alien, governed by physics so different that life as we know it could never exist. The source of this incredible diversity lies in the structure of the theory itself. String theory's extra dimensions are mathematically described by Calabi-Yau manifolds. Each Calabi-Yau manifold can be configured in many ways, with varying topologies and properties. Furthermore, the string vibrations and their interactions with these compact dimensions add additional layers of complexity. The combinations seem to stretch toward infinity, creating a landscape of possible universes rather than a single, definitive picture of reality. This then raises the question, why does our universe have the specific properties it does? The laws of physics in our universe are finely tuned in ways that seem almost miraculous. For example, the strength of the electromagnetic force, the masses of fundamental particles, and the cosmological constant are precisely the values needed to allow for the formation of stars, planets, and life. If these constants were even slightly different, the universe would be unrecognizable and likely uninhabitable. Out of all the possible vacuum states allowed by string theory, why do we find ourselves in one that supports life? One possible answer is the anthropic principle. This principle suggests that the universe must have the properties it does because otherwise we would not be here to observe it. In other words, life could only arise in a universe with the right conditions, so it is no surprise that we find ourselves in one of the rare states that permits life. The anthropic principle is controversial because it seems to sidestep deeper questions about why these specific conditions exist in the first place. Critics argue that it lacks predictive power and risks turning science into a kind of observational coincidence. Another possible explanation comes from the concept of a multiverse. If string theory's landscape represents all possible vacuum states, then perhaps every one of these states is realized in some part of a vast multiverse. In this view, our universe is just one of many, each occupying a different point in the landscape. Most of these universes would be barren and inhospitable, but a few, like ours, would have the right conditions for life. The multiverse idea offers a framework for understanding the apparent fine-tuning of our universe, but it also raises questions about how these other universes are connected and whether their existence can ever be tested or observed. The landscape problem also poses challenges for the predictive power of string theory. In physics, A successful theory should not only explain known phenomena, but also make specific predictions that can be tested through experiment or observation. With such a vast landscape of possible solutions, string theory struggles to make definitive predictions. For any given observation, there might be countless vacuum states that could potentially explain it. This lack of uniqueness has led some critics to question whether string theory can truly be considered a physical theory, as opposed to a mathematical framework. Despite these challenges, the landscape problem has also inspired new ways of thinking about fundamental physics. Researchers have developed techniques to explore the landscape systematically, searching for patterns and principles that might narrow down the possibilities. For instance, some scientists have investigated whether certain vacuum states are more stable or more likely to arise in the early universe. Others have looked for constraints imposed by symmetries or other fundamental principles that might rule out large portions of the landscape. One promising avenue of research involves using statistical methods to study the distribution of vacuum states. By treating the landscape as a kind of probability space, physicists can estimate how common certain features or properties might be. This approach has led to insights about which kinds of universes are most likely to emerge under different conditions, providing a way to connect the abstract mathematics of string theory with the physical realities of cosmology and particle physics. Another idea is the concept of a selection mechanism that might determine which vacuum state the universe settles into. In the early moments after the Big Bang, the universe was in a highly energetic and chaotic state, with quantum fluctuations playing a dominant role. It is possible that these fluctuations acted as a kind of natural selection process, favoring certain vacuum states over others based on their stability or other properties. This idea links the landscape problem to the dynamics of the universe's formation, offering a potential pathway for understanding why our universe has its specific characteristics. Some researchers have proposed that the same principles governing the landscape of string theory might also apply to the quantum structure of spacetime itself. This could provide new insights into phenomena like the holographic principle or the behavior of black holes, where the interplay between gravity and quantum mechanics creates some of the most puzzling mysteries in modern science. Taming singularities: how strings avoid the pitfalls of point particles. Singularities appear in two of the most puzzling contexts in physics: the center of black holes and the Big Bang. Both are situations where the force of gravity becomes so strong that even Einstein's general theory of relativity fails to provide a complete description, as does quantum mechanics. String theory offers a fundamentally new way to look at these problems. A point particle, when interacting with a singularity, essentially probes the spacetime at an exact point. At that point, if spacetime curvature is infinite, the equations governing the particle's behavior can no longer provide meaningful results. Strings, however, are extended objects. They have length, even if it is minuscule. This extended nature spreads out their interactions over a small but finite region of spacetime, softening the extreme effects of singularities. In the case of black holes, general relativity predicts that all the matter that forms a black hole collapses into a single point of infinite density at its center, called the singularity. The singularity represents a place where the laws of physics, as we currently understand them, come to an end. But in string theory, the very concept of a singularity may not exist. The extended structure of strings prevents the infinite collapse of matter into a zero-dimensional point. Instead, the collapsing matter might be spread out over a tiny but finite area or volume, forming what some researchers call a fuzzball. This fuzzball hypothesis, which arises from certain solutions in string theory, replaces the singularity with a complex, extended object made of strings and branes. This idea of avoiding singularities also applies to the Big Bang, which general relativity describes as the origin of the universe in a singular state of infinite density and temperature. According to classical physics, time itself began at the Big Bang, and trying to describe anything earlier than this moment is meaningless. String theory, however, offers a more nuanced picture. Instead of a singular point, the Big Bang may have involved a complex interplay of strings and higher dimensional objects in a highly energetic state. The initial conditions of the universe might have been governed by string interactions rather than a singular breakdown of space-time. One of the ways string theory avoids singularities is by introducing new degrees of freedom at extremely small scales. These degrees of freedom arise from the vibrations of strings, which encode a vast array of possible behaviors. Near a classical singularity, the energies involved are so high that the additional vibrational modes of strings come into play. These modes act as a kind of buffer, distributing energy and momentum over a wider area, and preventing the infinite collapse predicted by point particle theories. This mechanism effectively replaces the singularity with a region of high but finite curvature, where the behavior of space-time can still be described by physical laws. Also in string theory, the geometry of the extra dimensions can influence the behavior of strings in our familiar four-dimensional space-time. For example, strings may wrap around compactified dimensions, creating tension and energy that alter their interactions. These effects can smooth out the extreme curvatures associated with singularities, replacing them with more manageable structures. In some scenarios, the extra dimensions themselves may act as reservoirs of energy or information, absorbing the effects of a would-be singularity and redistributing them in a way that prevents breakdowns in the equations. Topology and string theory. How shape determines reality. Topology is a branch of mathematics concerned with the properties of shapes that remain unchanged under continuous transformations, such as stretching or bending, but not tearing or gluing. It examines the fundamental connectedness and structure of spaces, and in the context of string theory, it helps explain how the geometry and shape of extra dimensions influence the observable properties of our universe. The extra dimensions required by string theory are compactified into shapes often modeled as Calabi-Yau manifolds. They have a complex internal structure that is described by their topological properties. While these dimensions are too small to detect directly, their topology has profound effects on the physical laws we experience in our four-dimensional world. One of the most striking aspects of this connection is how the topology of these dimensions determines the types of particles that exist and the interactions between them. In string theory, the specific ways strings can vibrate depend on the shape of the compactified dimensions they inhabit. A more complex topology allows for a greater variety of vibrational patterns, which corresponds to a richer spectrum of particles and forces. For instance, the number of holes, twists, or other features in the topology of the extra dimensions directly influences the number of families of particles, such as quarks and leptons. This relationship emerges because the compactified dimensions control how strings wrap, twist, or resonate. The mathematics of topology, such as homology groups and Betti numbers, quantify these features and provide a direct link between the abstract shapes of higher dimensions and the tangible particles observed in particle physics experiments. The topology of the extra dimensions also affects the strengths and characteristics of fundamental forces like electromagnetism, the weak nuclear force, and the strong nuclear force. These forces are described in terms of fields, and the fields themselves are influenced by how the extra dimensions are twisted or curled. For example, gauge fields, which describe the interactions between particles, are determined by how strings interact with the topology of the compactified dimensions. Different topologies can result in different gauge symmetries, leading to variations in the way particles interact. Topology is especially important when considering symmetry breaking, a process that explains why some fundamental forces behave differently despite originating from a unified theory. In string theory, symmetry breaking can occur when the topology of the extra dimensions forces certain vibrational modes to take on specific configurations. These configurations can reduce the apparent symmetry of the forces, creating the distinctions we observe between, say, electromagnetism and the weak force. A key example of how topology shapes reality is found in the study of fluxes within compactified dimensions. Fluxes are quantities that describe how fields flow through the holes or cycles of a compactified space. In string theory, fluxes can stabilize the shapes of extra dimensions, preventing them from collapsing or expanding uncontrollably. The presence of fluxes also affects the energy landscape of the theory, determining which configurations of the universe are more likely to exist. This interplay between fluxes and topology is essential for understanding why our universe has its particular set of physical laws. Another fascinating aspect of topology in string theory is its connection to mathematical concepts like mirror symmetry. Mirror symmetry is a duality between pairs of Calabi-Yau manifolds with different topological properties. Despite their differences, these manifolds produce equivalent physical results when used in string theory. This symmetry has led to significant advances not only in theoretical physics, but also in pure mathematics, revealing deep connections between geometry, topology, and physics. Strings in the early universe. What they reveal about the Big Bang. In the moments immediately following the Big Bang, the universe was unimaginably hot and dense. The laws of physics as we know them break down under these conditions, creating a singularity. One of the central puzzles of the early universe is the phenomenon of inflation, a period of rapid expansion that occurred fractions of a second after the Big Bang. Inflation theory explains why the universe appears flat and uniform on large scales, and why the cosmic microwave background radiation, the faint glow left over from the Big Bang, is so smooth. However, the precise mechanism that triggered inflation remains unclear. String theory provides new possibilities by suggesting that the dynamics of strings and higher dimensional objects, like brains, could drive inflation. In string theory, brains are higher dimensional surfaces on which strings can attach and interact. During the early universe, the movement and interactions of these brains may have released enormous amounts of energy, driving the rapid expansion of space-time. Some versions of string theory propose that inflation began when two brains collided or moved apart, releasing the energy needed to inflate the universe. These interactions also produce ripples in space-time, which could leave imprints in the cosmic microwave background, offering a potential way to test these ideas. String theory's inclusion of multiple dimensions also opens new avenues for understanding the early universe. If the extra dimensions predicted by the theory were larger or differently shaped during the early moments of the universe, they could have influenced the way inflation unfolded. These dimensions might have stretched and compactified in tandem with the visible universe, shaping the large-scale structure we observe today. The specific topology of these extra dimensions could even explain anomalies in the CMB, such as slight variations in temperature that deviate from the predictions of simpler inflation models. As the universe expanded and cooled, energy condensed into matter, forming the building blocks of atoms and eventually stars and galaxies. In traditional physics, this process is described using quantum field theory, but at extremely high energies, quantum field theory encounters inconsistencies. String theory resolves these issues. During the high-energy phase after the Big Bang, strings would have vibrated at extremely high frequencies, creating heavy and exotic particles that no longer exist today. These particles could have played a crucial role in shaping the universe's evolution, influencing processes like baryogenesis, which explains why there is more matter than antimatter. If string theory's predictions are correct, some remnants of these processes might still be detectable as rare particles or subtle imprints in the cosmic microwave background. The CMB is a particularly valuable source of information for testing string theory's ideas about the early universe. This radiation, which has traveled to us from the time when the universe was about 380,000 years old, carries information about the conditions of the universe at that time. Tiny fluctuations in its temperature and polarization patterns are thought to be linked to quantum fluctuations that occurred during inflation. String theory predicts that the structure of these fluctuations might differ from the predictions of simpler models, providing a potential observational test for the theory. In addition to explaining inflation and particle production, string theory may also shed light on the nature of dark matter and dark energy. Some versions of string theory suggest that dark matter could be composed of particles arising from specific vibrational modes of strings. Similarly, the dynamics of strings and branes might explain the behavior of dark energy, which drives the accelerated expansion of the universe. String theory also offers a way to understand the initial conditions of the universe, why the Big Bang happened in the first place. In traditional cosmology, the Big Bang is treated as a starting point, but string theory hints at deeper origins. Some models suggest that the universe emerged from the interaction of higher dimensional objects or from a quantum fluctuation in a pre-existing spacetime. These ideas challenge the notion of the Big Bang as a singular event, replacing it with a more dynamic and interconnected picture of the universe's birth. String theory also provides a framework for understanding the ultimate fate of the universe. Just as the early universe was dominated by the dynamics of strings and branes, these objects may continue to influence its evolution on cosmic timescales. By studying the connections between string theory and the early universe, scientists may uncover principles that govern not only the universe's past, but also its long-term future. Whether the universe will expand forever, collapse back into a singularity, or transition into a new phase of existence may depend on the underlying structure of strings and the topology of spacetime. Cosmic strings, relics of a higher dimensional past. Cosmic strings, if they exist, represent a link between the early universe and the theories that aim to describe its fundamental nature. These hypothetical structures are not the same as the one-dimensional strings described in string theory, but they are conceptually related. Both share the idea that the universe might be shaped by entities extending beyond the point-like objects of traditional particle physics. In the case of cosmic strings, their origins are thought to lie in the high-energy conditions of the early universe, acting as relics of phase transitions that occurred as the universe cooled. To understand cosmic strings, it's useful to think about phase transitions in the context of familiar examples. Water, for instance, undergoes phase transitions when it freezes into ice or boils into steam. In the early universe, something similar happened on a cosmic scale. But instead of water and ice, the transitions involved fundamental fields and forces. When the universe was extremely hot, forces like electromagnetism and the weak nuclear force were unified, behaving as a single interaction. As the universe expanded and cooled, these forces separated in a series of phase transitions, much like water crystallizing into ice. These transitions, however, were far from smooth. Just as imperfections can form in the freezing of water, such as cracks in ice, imperfections can arise during cosmic phase transitions. In the early universe, these imperfections could have taken the form of cosmic strings. These strings are not physical objects like the strings in a guitar or the strings of string theory, but rather are regions of energy density where the field did not settle into its lowest energy state. In effect, they are defects left behind in the structure of spacetime. Cosmic strings are theorized to be incredibly thin, stretching across vast distances while having immense energy and mass. Their formation is thought to be tied to symmetry-breaking events, which are key features of many grand unified theories in physics. When symmetries break, the laws of physics that once appeared uniform can start behaving differently in different regions. These breaking points can create boundaries, and cosmic strings might form along these boundaries, threading through spacetime as narrow, one-dimensional lines of concentrated energy. In the early universe, matter was distributed in a nearly uniform manner, with tiny fluctuations providing the seeds for future galaxies and clusters. Cosmic strings, if present, could have acted as gravitational scaffolds, pulling matter toward them and amplifying these initial fluctuations. Their immense energy and mass would have created strong gravitational fields, influencing the movement of nearby matter, and possibly leaving imprints that we could observe today. If cosmic strings were present in the early universe, their gravitational effects might have created unique patterns in the CMB. For instance, as a cosmic string moves through space-time, it could distort the light coming from the CMB, producing a distinct signature known as the Kaiser-Stebbins effect. These distortions would appear as sharp, linear discontinuities in the otherwise smooth radiation, offering a potential way to detect cosmic strings. Despite extensive searches, no definitive evidence for cosmic strings has been found in the cosmic microwave background or elsewhere. This absence has placed strict limits on the properties that cosmic strings could have if they do exist, such as their tension and energy scale. However, this lack of direct observation does not rule out their existence entirely. It's possible that cosmic strings are simply more subtle than expected, interacting with the universe in ways that are harder to detect. In some versions of string theory and related frameworks, cosmic strings could be the macroscopic manifestations of fundamental strings or branes from higher dimensions. This idea blurs the line between the strings of string theory and the cosmic strings of cosmology, suggesting that the two might be different scales of the same underlying phenomenon. If true, studying cosmic strings could offer a window into the higher dimensional past of the universe, revealing insights about the conditions that shaped its earliest moments. One also wonders about the fate of these relics in a universe that has been expanding and evolving for billions of years. Over time, strings would lose energy through interactions and the emission of gravitational waves, potentially shrinking and disappearing. However, the processes governing their evolution are complex and depend on factors like the density of strings in the early universe and their interactions with matter and radiation. Some models predict that cosmic strings could still exist today, albeit in smaller numbers and at lower energy scales than in the early universe. How string theory influences inflationary models. Cosmic inflation is one of the most important ideas in modern cosmology, describing a period of rapid expansion that occurred in the universe's earliest moments. While inflation explains many observed features of the universe, such as its large-scale uniformity and the origin of cosmic structure, it leaves many questions unanswered. String theory, with its rich mathematical framework and higher dimensional insights, has offered a unique perspective on inflation, providing tools to refine and expand our understanding of this critical phase. In the simplest models, inflation is driven by a scalar field, a type of field that assigns a single value to every point in space and time. This field, often called the inflaton, rolls down a potential energy landscape, fueling the universe's exponential growth. Once it settles into a stable state, inflation ends, and the energy stored in the field transforms into particles, initiating the hot, dense state we associate with the Big Bang. While this description works well at a basic level, it raises further questions about the nature of the inflaton field, its potential energy, and why the universe underwent inflation in the first place. String theory steps into this discussion by offering a framework in which scalar fields naturally arise. These fields often appear as part of the process of compactifying extra dimensions. In string theory, the specific way these dimensions are compactified determines the properties of scalar fields in the lower dimensional world we observe. These fields can play the role of the inflaton, and their dynamics during the early universe can drive inflation. One of the contributions of string theory to inflationary models is the potential for complex and varied inflationary scenarios. In the simplest inflationary models, the potential energy landscape of the inflaton is relatively smooth, guiding the field's evolution in a predictable way. However, the extra dimensions and branes in string theory introduce far more intricate structures into this landscape. Scalar fields associated with the geometry of these extra dimensions may face rugged potential energy surfaces, filled with valleys, peaks, and plateaus. These features can give rise to novel forms of inflation, such as brane inflation, where the movement of branes through extra-dimensional space generates the required expansion. In this scenario, the inflaton field corresponds to the distance between branes or between a brane and an anti-brane in higher dimensional space. As these objects move toward each other, their interaction generates a potential energy that drives inflation. When the branes collide, inflation ends, and the energy released in this collision populates the universe with particles. This mechanism not only provides a way to realize inflation, but also ties it directly to the fundamental ingredients of string theory, offering a potential bridge between cosmology and the microscopic world of strings and branes. The intricate potential energy landscapes in string theory also allow for inflationary models that deviate from the simplest scenarios, producing unique observational signatures. For example, models inspired by string theory can predict small deviations in the spectrum of density fluctuations left behind by inflation. These fluctuations, observed in the CMB, are a key source of information about the universe's earliest moments. While standard inflationary models predict nearly Gaussian fluctuations, some string-inspired models can introduce non-Gaussian patterns, offering a potential way to test these ideas against observations. Another contribution is its ability to address some of the challenges faced by conventional models, such as the fine-tuning problem. Inflationary models often require the inflaton field to start in a specific configuration with just the right properties to drive inflation. Critics argue that this setup seems contrived, requiring careful adjustment of initial conditions. String theory, with its vast landscape of possible solutions, provides a framework where such configurations might naturally emerge. In this landscape, the parameters of the inflaton field, including its initial value and potential energy shape, are determined by the geometry and dynamics of compactified dimensions, potentially reducing the need for fine-tuning. However, the string theory landscape itself introduces a new set of challenges. The sheer number of possible solutions makes it difficult to pinpoint which scenario corresponds to our universe. This vastness complicates efforts to make specific predictions about inflationary dynamics and observable consequences. Yet, it also opens the door to the idea of a multiverse, where different regions of the universe might realize different solutions from the string theory landscape. String theory also sheds light on the nature of quantum fluctuations during inflation. These fluctuations, which arise from the Heisenberg uncertainty principle, are stretched to macroscopic scales by the rapid expansion of the universe. They form the seeds for all cosmic structures, from galaxies to clusters. In string-inspired models, the behavior of these fluctuations can be influenced by the higher dimensional geometry and the dynamics of branes. One of the most ambitious goals of connecting string theory to inflation is to address the quantum gravity problem. Inflation involves energy scales close to the Planck scale, where quantum effects on gravity become significant. String theory, as a candidate for a quantum theory of gravity, provides tools to explore these regimes. Despite its promise, the incorporation of string theory into inflationary cosmology is far from complete. Many of the models remain highly theoretical, with key aspects depending on assumptions about the nature of extra dimensions, branes, and the string landscape. Experimental evidence for these ideas, such as the detection of non-Gaussian patterns or gravitational waves from inflation, also remains elusive. Can we test string theory? The quest for observable evidence. The question of whether string theory can be tested lies at the heart of its scientific legitimacy. For decades, string theory has dazzled physicists with its elegant mathematical framework and its potential to unify all fundamental forces of nature. Yet the lack of direct observable evidence has also been a point of contention. Testing string theory presents a unique challenge because the energy scales at which strings operate are vastly beyond what current technology can probe. One major obstacle to testing string theory is the minuscule size of the strings themselves. These fundamental objects are thought to be about 10 to the power of minus 35 meters in length, a scale known as the Planck length. Observing anything at this scale directly would require energies far greater than those achievable by even the most powerful particle accelerators, like the LHC. For perspective, the LHC operates at energies around 14 tera-electronvolts, but probing the Planck scale would require an accelerator the size of the galaxy. This energy gap makes direct detection of strings or their vibrations unlikely in the near future. Despite this limitation, physicists have sought ways to test string theory indirectly by looking for its signatures in phenomena we can observe. One promising avenue lies in the study of high-energy particle collisions. In string theory, the interactions between particles are mediated by strings, and at sufficiently high energies, these strings could leave imprints in the form of distinctive scattering patterns or unexpected resonances. Future particle accelerators, such as the proposed Future Circular Collider, FCC, or the International Linear Collider, ILC, may achieve the higher energy levels needed to explore this uncharted territory. The early universe, with its extreme temperatures and densities, represents a natural laboratory for high-energy physics. String theory predicts phenomena that could have shaped the universe's evolution, leaving observable traces in the CMB. For instance, certain models of string theory predict the existence of additional scalar fields that could influence the patterns of temperature fluctuations in the CMB. By analyzing these patterns with increasing precision, scientists will hopefully uncover hints of string theory's influence on the cosmos. String theory predicts that spacetime itself may have a more complex structure, with additional dimensions and stringy effects modifying how gravitational waves propagate. Advanced detectors like LIGO and Virgo have already made groundbreaking observations of gravitational waves, and future upgrades might reveal subtle deviations from general relativity's predictions, deviations that could point to string theory's influence. These could include unique polarization patterns or frequency-dependent effects that arise from the underlying string dynamics. String theory provides a microscopic explanation for black hole entropy, and it predicts new phenomena in extreme gravitational environments. For instance, certain types of black holes might emit distinctive signals as they interact with surrounding matter, signals that could reveal the presence of extra dimensions or the stringy nature of space-time. While these effects are subtle and challenging to measure, advances in observational techniques, such as high-resolution imaging of black hole event horizons, could bring these predictions within reach. Supersymmetry, a key component of many string models, proposes a symmetry between fermions and bosons. If supersymmetry exists, every known particle would have a heavier superpartner. While the LHC has not yet detected these superpartners, their discovery would provide strong evidence supporting string theory. Additionally, string theory predicts the existence of particles called axions, which could account for dark matter. Experiments designed to detect axions, such as those using ultra-sensitive magnetic fields, are actively underway and could provide crucial insights. In high-energy collisions, the LHC might create Kaluza-Klein particles, hypothetical particles that arise from compactified dimensions, which would appear as heavy versions of known particles, such as the photon or gluon. Detecting such particles would provide indirect evidence for the existence of extra dimensions and support the framework of string theory. Moreover, the properties of these particles, such as their masses and lifetimes, could reveal details about the shape and size of the compactified dimensions, shedding light on the hidden geometry of the universe. The study of neutrinos, elusive particles that barely interact with matter, also holds promise for testing string theory. Neutrinos are sensitive to effects from extra dimensions, and precise measurements of their properties, such as masses and mixing angles, could reveal deviations consistent with string predictions. Neutrino observatories like IceCube in Antarctica are pushing the boundaries of what we can learn about these ghostly particles and their connection to the underlying theory of everything. Quantum computers, with their ability to simulate complex quantum systems, could provide new tools for exploring the predictions of string theory in ways that were previously impossible. At the same time, theorists are refining the mathematical framework of string theory, identifying potential signatures that might be observable even at lower energies. String theory also predicts the existence of entirely new phenomena that could be observed in particle accelerators. One such phenomenon is the possible formation of microscopic black holes. If the energy of particle collisions surpasses a certain threshold, and if extra dimensions exist, it might be possible to create tiny black holes in the lab. These black holes would decay almost instantly, releasing a cascade of particles that detectors could measure. While this idea may sound exotic, it is rooted in well-established physics, combining principles of general relativity and quantum mechanics. The observation of microscopic black holes would be a groundbreaking discovery, providing direct evidence of extra dimensions and the stringy nature of space-time. Critics of string theory often point to its vast landscape of solutions as a challenge to its testability. The theory allows for an enormous number of possible vacuum states, each corresponding to a different set of physical laws. This vastness has led some to argue that string theory makes too many predictions, diluting its scientific utility. However, proponents see the landscape as an opportunity, suggesting that statistical methods could identify the most likely vacua consistent with our universe's observed properties. This approach has already yielded insights into why certain constants of nature, like the strength of the electromagnetic force, take their observed values. Of course, history has repeatedly shown that major breakthroughs often arise from serendipitous discoveries rather than planned experiments. As observational and experimental techniques continue to advance, new phenomena could emerge that align with string theory's predictions in surprising ways. Gravitational waves and string theory, a match made in space-time. First predicted by Einstein's theory of general relativity and directly observed for the first time in 2015, gravitational waves are generated by massive objects in motion, such as merging black holes or neutron stars. The study of gravitational waves offers insights into the nature of gravity, the behavior of space-time under extreme conditions, and potentially the predictions of string theory. While string theory operates on scales much smaller than the wavelengths of observed gravitational waves, its framework provides mechanisms that could influence these cosmic signals in ways detectable with precise instrumentation. In string theory, the graviton naturally arises as a vibrational mode of a closed string. Gravitational waves, as macroscopic manifestations of gravitational phenomena, provide an indirect way to explore the properties of gravitons and test string theory's predictions. At extremely high energies, such as those present in the early universe or during violent astrophysical events, string theory suggests that deviations from classical general relativity might occur. These deviations could manifest as subtle changes in the properties of gravitational waves. For instance, string theory predicts that the existence of additional spatial dimensions could alter the propagation of gravitational waves. If extra dimensions are present, gravitational waves might leak into them, leading to energy loss or changes in wave patterns that could be detected by advanced observatories like LIGO, Virgo, or the upcoming Laser Interferometer Space Antenna, or LISA. LISA, designed to detect gravitational waves with much longer wavelengths than ground-based detectors, is particularly suited to test string theory. Unlike the shorter wavelength waves generated by merging stellar mass black holes, LISA will focus on signals from supermassive black hole mergers and other large-scale cosmic events. These signals could carry imprints of physics beyond general relativity, including signatures of string theory. If gravitational waves travel through a universe with additional dimensions, their amplitudes, frequencies, or polarizations could show anomalies compared to predictions based solely on Einstein's equations. Shortly after the Big Bang, the universe underwent inflation, during which quantum fluctuations were stretched to macroscopic scales, generating a stochastic background of gravitational waves. String theory, with its additional dimensions and extended objects like strings and branes, might modify the dynamics of inflation, influencing the spectrum of these primordial gravitational waves. Detecting such a spectrum could reveal clues about the fundamental nature of spacetime and provide indirect evidence for the structures predicted by string theory. Another fascinating possibility arises from cosmic strings. These defects could generate gravitational waves as they oscillate or interact, producing signals detectable by observatories. If cosmic strings were found, their properties, such as tension and energy density, could provide insights into high-energy physics and potentially point towards string theory's validity. In addition to cosmic strings, string theory predicts a variety of exotic phenomena that could influence gravitational wave observations. For example, certain models suggest the existence of axion-like particles or scalar fields associated with string theory's compactified dimensions. These fields could couple to gravitational waves, causing effects such as altered dispersion relations or changes in wave polarization. Such interactions might leave detectable traces in the data collected by gravitational wave observatories, offering a new way to probe the theory's predictions. Black holes provide a natural testing ground for string theory. Some string-inspired models propose that black holes might be replaced by extended objects, such as fuzzballs, which lack a singular core. These models could lead to subtle differences in the gravitational waves emitted during black hole mergers, such as slight deviations in the ring-down phase, the period after the merger when the newly formed black hole settles into a stable state. Detecting these deviations would provide an indirect glimpse into the quantum structure of black holes and their connection to string theory. Astrophysical signatures of strings in the cosmos. The potential existence of certain astrophysical signatures, like cosmic strings, could serve as direct or indirect evidence of the theory's predictions. If cosmic strings exist, they could produce observable effects in the cosmos. One such signature would be their influence on light and matter passing near them. Due to their immense energy density, cosmic strings would warp the fabric of space-time around them, acting like cosmic magnifying glasses. This effect, known as gravitational lensing, could cause the light from distant stars or galaxies to bend in characteristic ways. Astronomers have been searching for these unique lensing patterns, often described as double images or other distortions, in large-scale surveys of the sky. If such patterns are detected, they could provide indirect evidence for the existence of these mysterious structures. Unlike stationary objects, cosmic strings are expected to vibrate, oscillate, and even interact with one another. When two strings collide, they might reconnect or form loops, which could oscillate and gradually lose energy by emitting gravitational waves. These gravitational waves would have specific frequencies and patterns that could be detected by gravitational wave observatories. While brains are typically considered to exist on scales far smaller than what we can currently observe, some models propose that their effects might manifest on cosmic scales. For example, brains could influence the dynamics of the universe's expansion or leave imprints on the CMB. Subtle anomalies in the temperature and polarization patterns of this radiation, detected by missions like the Planck satellite, could provide clues about the presence of higher dimensional structures. Gamma-ray bursts, some of the most energetic events in the universe, have also been considered potential testing grounds for string theory's predictions. These bursts are thought to originate from cataclysmic events like the collapse of massive stars or the merging of neutron stars, releasing immense amounts of energy in the form of high-energy photons. Some models of string theory propose that the properties of these photons, such as their polarization or dispersion, might be affected by the presence of extra dimensions or quantum gravity effects. By carefully studying the light from gamma-ray bursts, scientists could uncover hints of these subtle influences. Astrophysical observations of dark matter and dark energy also provide potential connections to string theory. Some models suggest that dark matter could consist of exotic particles or fields predicted by string theory, while dark energy might arise from the dynamics of compactified dimensions or higher dimensional brains. By studying the distribution and behavior of dark matter in galaxies, or the accelerating expansion of the universe driven by dark energy, scientists hope to find clues that link these phenomena to the predictions of string theory. Neutron stars, the remnants of massive stars that have undergone supernova explosions, offer yet another avenue for testing string theory's predictions. These incredibly dense objects, composed mostly of neutrons packed tightly together, are among the most extreme environments in the universe. String theory's extended objects and higher dimensional framework might influence the behavior of matter under such extreme conditions, leading to observable effects in the emission of light, neutrinos, or gravitational waves from neutron stars. Detecting these effects could provide indirect evidence for the theory's validity and shed light on the fundamental nature of matter and energy. Is string theory science or philosophy? Debates in the physics community. Despite its profound elegance and ambitious aims, string theory occupies a unique and often controversial position within the scientific community. It aspires to be a theory of everything. Yet this lofty goal comes with significant challenges, particularly when it comes to the question of testability. For some, string theory's abstract nature evokes a sense of wonder, offering a glimpse into the universe's underlying order. For others, it strays too far from empirical science, venturing into speculative territory. These challenges have sparked a long-standing debate. Is string theory a legitimate scientific framework, or does it drift too far into the realm of philosophy? One of the primary criticisms leveled against string theory is its apparent lack of experimental evidence. Unlike other successful scientific theories, such as Einstein's relativity or the standard model of particle physics, string theory has not made any definitive predictions that can be tested in the laboratory. Its most striking features, extra dimensions, supersymmetric particles, and vibrating strings at the Planck scale, remain beyond the reach of current technology. Without direct experimental validation, critics argue, string theory risks becoming a mathematical exercise rather than a physical theory. Traditionally, a scientific theory must make falsifiable predictions, statements that can be tested and potentially disproven through observation or experiment. String theory, however, operates on a level of complexity that makes falsifiability difficult to achieve. The theory allows for a vast number of possible solutions, each corresponding to a different set of physical laws and constants. Critics argue that this flexibility undermines its scientific credibility. Defenders of string theory counter that its mathematical consistency and explanatory power should not be dismissed. They argue that it represents a natural extension of the principles of physics, providing a framework that unifies gravity with the quantum world. Even if experimental evidence remains elusive, string theory has already contributed to significant insights in theoretical physics. For example, the development of dualities and the holographic principle have provided new perspectives on various natural phenomena. These advances suggest that string theory has value as a tool for exploring the boundaries of our understanding, even if it has yet to deliver definitive empirical results. Advocates argue that science often progresses in stages, with theoretical developments preceding experimental breakthroughs. Historical examples, such as the prediction of gravitational waves by general relativity decades before their detection, highlight the patience required in the pursuit of ambitious scientific goals. String theory, they suggest, may be in a similar phase of development, awaiting future technologies that could unlock its mysteries. String theory is often praised for its mathematical beauty and internal consistency, qualities that have historically guided physicists toward successful theories. Einstein, for instance, was driven by a belief in the harmony of the natural world, a principle that shaped his formulation of general relativity. String theorists argue that the elegance of their framework should not be dismissed, as it suggests an underlying truth waiting to be discovered. Critics, however, caution against relying too heavily on aesthetics, pointing out that nature does not always conform to human notions of beauty. They argue that scientific progress requires rigorous testing and empirical validation, not just elegant equations. As one of the most popular research areas in theoretical physics, string theory has attracted a large and dedicated community of scientists. This dominance has led to concerns about intellectual monoculture, where alternative approaches to quantum gravity may receive less attention and funding. Some critics worry that string theory's prominence reflects not its scientific merits, but its ability to capture the imagination of researchers and funding agencies. Proponents, on the other hand, argue that the widespread interest in string theory reflects its potential to address some of the most profound questions in physics. They view the diversity within the string theory landscape itself, with its multiple approaches and subfields, as a strength rather than a weakness. Its proponents acknowledge the challenges of testing its predictions, but emphasize the importance of pushing the boundaries of knowledge. Its mathematical framework has already influenced other areas of science, from condensed matter physics to mathematics itself. Even if string theory ultimately proves incomplete or incorrect, the insights gained from its development may pave the way for new breakthroughs and discoveries. Anthropic principle versus predictive power. Can string theory deliver? The anthropic principle occupies a curious space in the world of scientific theories, offering a lens through which we might understand the universe's finely tuned properties. In essence, it posits that the laws of nature and the constants of the universe are such as they are because they allow life to exist, particularly intelligent observers capable of contemplating these laws. Within the context of string theory, the anthropic principle has gained traction largely because of the theory's vast landscape of possible solutions. This landscape, a nearly incomprehensible number of vacuum states or configurations that arise from the compactification of extra dimensions, creates a challenge. Why does our universe appear to have such precise conditions for life, given the near-infinite range of possibilities? String theory, by its nature, doesn't dictate a single inevitable version of the universe. Instead, it predicts a multitude of potential universes, each with its own distinct physical laws. The anthropic principle becomes a possible explanation. Out of the myriad configurations in the string theory landscape, we happen to inhabit one that allows life to exist because, quite simply, we wouldn't be here to observe it otherwise if it didn't. For some, the anthropic principle offers a comforting way to reconcile the apparent fine-tuning of the universe with the immense possibilities offered by string theory. It provides an explanation for why the universe is the way it is, without requiring every detail to be derived from first principles. In this view, the landscape of string theory becomes not a flaw, but a feature, an acknowledgement that our universe is part of a much larger multiverse, one in which other regions or universes might operate under entirely different rules. The anthropic principle then serves as a filter, highlighting those universes capable of supporting intelligent observers. Critics argue that it undermines one of the fundamental goals of physics, to make precise, testable predictions about the universe. Science, as traditionally understood, seeks to uncover universal laws that apply consistently across time and space. The anthropic principle, by contrast, can feel more like an after-the-fact observation than a predictive framework. Instead of providing a mechanism for why certain constants take their specific values, it suggests that they simply do because we exist to measure them. This shift can be unsettling for those who view physics as a pursuit of deeper truths rather than convenient explanations. When considering the vastness of the string landscape, how can physicists identify the one that corresponds to our universe? Some researchers hope to narrow the landscape by finding criteria, mathematical constraints, or physical mechanisms that reduce the number of viable vacuum states. Others, however, see the sheer size of the landscape as evidence that prediction in the traditional sense may no longer be possible. If the constants of nature are determined by chance, through a kind of cosmic lottery across the multiverse, then the role of string theory shifts from predicting unique outcomes to describing the broader framework within which those outcomes arise. Should a theory be judged solely by its ability to make predictions, or can it also be valued for the explanatory depth it provides? String theory, even with its reliance on the anthropic principle, offers profound insights into the nature of reality, the origins of physical laws, and the structure of space-time. It provides a unifying framework that brings together quantum mechanics and general relativity, two of the most successful but previously incompatible theories in physics. For some, this unification is reason enough to pursue string theory, regardless of its immediate predictive power. Yet, the lack of clear predictions remains a challenge. Physicists are working to address this issue in several ways. One approach involves identifying patterns or statistical tendencies within the string landscape. Instead of searching for a single definitive solution, researchers look for clusters of solutions that share certain properties. For example, they might explore whether the landscape naturally favors universes with properties similar to ours, such as 3 large spatial dimensions and a small but non-zero cosmological constant. If such patterns can be identified, they could provide indirect evidence that string theory aligns with the observed universe, even if it cannot pinpoint our specific configuration. Another approach involves the development of testable predictions that might arise from the broader framework of string theory, rather than from its detailed solutions. For example, string theory predicts the existence of supersymmetry, a symmetry that would extend the standard model of particle physics by introducing a partner particle for every known particle. If supersymmetric particles were discovered in experiments, such as those conducted at the LHC, it would provide strong support for string theory, even if it did not directly confirm the anthropic principle or the multiverse. For some, this probabilistic view is liberating, opening the door to new ways of thinking about the cosmos. It invites us to see our universe not as a unique or special entity, but as one thread in a vast, interconnected tapestry of possibilities. For others, however, it feels like a retreat from the core mission of physics, to uncover the deep, underlying principles that govern all of existence. The debate over the anthropic principle thus reflects a deeper tension within the scientific community. Beyond strings, what lies ahead in theoretical physics? While string theory has driven theoretical physics forward for decades, it remains a work in progress. Its mathematical intricacies, untested predictions, and vast landscape of possible solutions leave room for alternative or complementary approaches to emerge. The search for the next step in understanding the universe is already underway, exploring ideas that challenge current frameworks, refine existing theories, or offer entirely new ways of thinking about reality. One avenue that physicists are investigating involves going beyond the strings themselves. M-theory incorporates objects called branes that can range from two-dimensional surfaces to objects with even higher dimensions, collectively referred to as p-branes. A two-brane, for instance, is like a sheet, while a three-brane resembles a volume, and so on. Our entire observable cosmos might reside on a three-dimensional brane, floating in a higher dimensional bulk. In this scenario, the extra dimensions of string theory could be far larger, hidden from view because we are confined to our brane. Gravity, which is inherently weaker than the other forces, might be the only interaction capable of leaking into the higher dimensional bulk, potentially explaining its relative weakness compared to electromagnetism or nuclear forces. These ideas open doors to profound questions. Are there other branes with their own universes? Could we ever detect the effects of these hidden dimensions? Another concept that has captured the attention of physicists is the idea of emergent spacetime. Traditionally, space and time are treated as the fundamental backdrop for all physical events. In general relativity, spacetime is dynamic, bending and stretching in response to the presence of mass and energy. String theory takes this a step further, describing spacetime as a consequence of the underlying strings and their interactions. But some physicists are now exploring the possibility that spacetime itself is not fundamental but emergent, arising from a deeper, more abstract structure. One analogy often used is that of temperature in a gas. While temperature feels like a fundamental property to us, it is actually an emergent phenomenon resulting from the collective motion of countless individual molecules. Similarly, spacetime might emerge from a more fundamental set of rules or entities, such as networks of quantum entanglement or other pre-geometric constructs. This shift in perspective could resolve some of the biggest puzzles in physics, such as what happens at the singularities of black holes or the Big Bang, where traditional notions of space-time break down. Quantum gravity remains a key focus in the search for what lies beyond string theory. While string theory is a leading candidate for a quantum theory of gravity, other approaches exist. Loop quantum gravity, for example, takes a different route by attempting to quantize space-time itself rather than introducing strings or extra dimensions. In loop quantum gravity, space-time is composed of discrete building blocks, akin to a lattice or network. These quantum loops form the fabric of the universe, eliminating the infinite densities that plague classical descriptions of black holes and the Big Bang. While less ambitious in scope than string theory, loop quantum gravity has the advantage of being more closely tied to testable predictions about space-time's behavior at microscopic scales. The holographic principle, which emerged from studies of black hole entropy, implies that the three-dimensional world we experience might be a projection of information stored on a two-dimensional surface. The ADS-CFT correspondence provides a concrete example of this idea by equating a gravity theory in a higher dimensional space with a quantum field theory in a lower dimensional one. Physicists are now exploring whether holography could apply to our universe as a whole, providing a new framework for understanding quantum gravity and space-time. As these ideas evolve, the role of mathematics in theoretical physics continues to grow. String theory, with its reliance on advanced geometry, topology, and algebra, has already pushed the boundaries of what mathematicians and physicists can achieve together. Future developments may require even more innovative mathematical tools, especially as researchers delve into the intricate structures of higher dimensional spaces, quantum networks, and emergent phenomena. The interplay between mathematics and physics is likely to become even more central, with breakthroughs in one field often driving progress in the other. Experimentation, too, will play a crucial role in shaping the future of theoretical physics. Advances in particle accelerators or cosmic ray observatories might reveal subtle deviations from the standard model, hinting at the influence of supersymmetric particles or other phenomena predicted by string theory. The legacy of string theory. Will it redefine our universe forever? String theory, whether it ultimately proves to be the final answer to the universe's mysteries or simply a chapter in a longer story, has already left a profound legacy. Its influence extends far beyond the boundaries of theoretical physics, reshaping how scientists and mathematicians think about reality. For centuries, physicists have sought to bring the fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, under a single theoretical framework. Even if the theory's specific framework proves incomplete, the pursuit itself has inspired countless other ideas in physics. Mathematically, string theory has been nothing short of revolutionary. Its equations require tools from areas of mathematics that were previously seen as abstract or unrelated to physics. Concepts like Calabi-Yau manifolds, modular forms, and topological field theories have become central to string theory's development, forging new connections between mathematics and the physical world. This cross-pollination has been mutually beneficial. Mathematicians have drawn inspiration from problems posed by string theory, leading to breakthroughs in pure mathematics, while physicists have gained access to new techniques for solving their equations. One of the most famous examples of this interplay is the discovery of mirror symmetry. This phenomenon, initially observed in string theory, revealed a deep equivalence between seemingly different Calabi-Yau spaces. Mathematicians later formalized mirror symmetry, using it to solve problems in algebraic geometry that had been unsolved for decades. String theory's ability to uncover such hidden relationships has led some to describe it as a theory-generating machine, providing insights even in areas far removed from its original goals. Traditional physics focuses on making precise predictions that can be tested through experiments. String theory, with its emphasis on unification and mathematical beauty, has challenged this paradigm. Its inability to make clear, testable predictions has drawn criticism, but others see this as a strength, suggesting that string theory represents a new kind of theoretical physics, one that prioritizes conceptual and mathematical coherence. The challenges string theory poses are so complex that they require expertise from multiple fields. Physicists, mathematicians, and computer scientists have come together to tackle its problems, creating a model for how modern science can address big questions. The rise of large-scale collaborations in string theory mirrors similar trends in experimental physics, like the teams behind the Large Hadron Collider or gravitational wave detectors. This collaborative spirit is likely to persist, influencing how future generations approach scientific discovery. String theory has also captured the public's imagination in ways few scientific theories do. Its ideas about extra dimensions, parallel universes, and the ultimate nature of reality have inspired countless books and documentaries. String theory's influence is unlikely to fade. It has already inspired a generation of physicists, many of whom have gone on to explore related areas like quantum gravity or the nature of dark matter and dark energy. Even if string theory itself does not provide the final answer, its ideas and methods will continue to shape how physicists approach fundamental questions. Just as quantum mechanics and general relativity grew out of earlier theories, the next great breakthrough in physics may build on the foundation string theory has laid. But now, this journey comes to an end. What other theories would you like to hear about? Send us your ideas in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.